Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
So this now we come to the serrated character of the curve C in that previous slide. The serrated character of the curve C in figure, sometimes observed in the plain carbon steel and alloys and certain aluminum alloys, for example, aluminum magnesium alloys, can also be explained in terms of dislocation solute atom interactions that we have seen. Curve C is inhomogeneous in nature but does not have the distinct horizontal segment that characterizes the upper and lower yield point phenomenon CA. Bursts of mechanical twin formation and growth are one possible cause of the serrated behaviors in C. Dislocation motion is the dominant or the only plasticity mechanism active under normal loading conditions. In these cases, the appearance of curve C is known as Poitevin-Le Chatelier effect, and this is evidence of dynamic strain aging. Okay, so this particular serrated flow of materials or serrated flow exhibited by the stress strain curve is a phenomenon called dynamic strain aging. Okay, so we are discussing two things here. Either it could be a solute dislocation interaction, pinning, unpinning, and then again it comes out of the atmosphere and relaxes and then repin. Then also this kind of serrated flow comes, or it could be a pin, bursts of pin formation or rather nucleation and growth. This also will cause the serrated behavior. As long as the diffusion rate for the solute atom is equal to or slightly greater than the rate of plastic deformation, dislocations will alternatively break free from the solute atmospheres and then be repinned. Just I said before, as long as this can happen, pinning, repinning, okay, so the serrated flow will keep on occurring till the end of the fracture, producing the serrated curve C. If the strain rate and the test temperature were outside the critical range, homogeneous dislocation flow would take place since solute atmosphere formation would no longer be favored. Accordingly, the stress strain curve would be smooth. Okay. Dynamic strain aging can cause poor surface quality and reduced ductility associated with the formation of undesirable surface marks like Luder bands. So it is preferable to avoid it through careful alloy selection and choice of processing condition when possible. So like we discussed in the case of Luder bands, the dynamic strain aging also going to leave a poor surface quality. So we need to select the appropriate processing or alloy design or other conditions to overcome this. Okay, that's about the yield point phenomenon and strain aging. Just briefly we looked at. Now we go to effect of strain rate on flow properties. Suppose how the strain rate is going to get affected. The rate at which the strain is applied to a specimen can have an important influence on the flow stress. The strain rate is defined as epsilon dot, which is d epsilon by dt, and it is conventionally expressed in units of per second. The spectrum of available strain rate is given in this table. So what are the typical strain rates we come across? The 10 to the power minus 8 to 10 to the power minus 5 per second, typically used in the creep test at constant load or constant stress. 10 to the power minus 5 to 10 to the power minus 1 per second. A static tension test with hydraulic or screw driven machines. 10 to the power minus 1 to 10 to the power 2 per second, which is a dynamic tension or compression test. and 10 to the power 2 to 10 to the power 4 high speed testing using impact bots must consider wave propagation effects because we are dealing with very high strain rate. 10 to the power 4 to 10 to the power 8 is hypervelocity impact using gas guns or explosively driven projectiles, shock wave propagations. So these are the typical strain rate ranges, and the corresponding test is given, which is very important. You should know this. And most of the tension tests are done with the initial strain rate. You have to understand that it is not. You can also do the constant strain rate experiments, but it is conventionally or normally it is not done in every laboratory. It is always considered the initial strain rate that you have to remember. So this is a flow stress at a strain of 002 versus strain rate for 6063 aluminum alloy. You can see that at various temperatures, stress versus strain rate, you can see that how the strain rate, as the temperature, for a given temperature, with the increased strain rate, the stress increases. Okay. Of course, the temperature, the sigma, the temperature is lowered, the sigma increases. That also we know. So this is what it's shown here. The yield stress and flow stress at low plastic strains are more dependent on strain rate than the tensile strength. Okay, so this is what it is. The yield strength and the flow stress at lower plastic strain. High rates of strain cause the yield point to appear in tests on low carbon steel that do not show a yield point under ordinary rates of loading. Okay, this is another interesting point of that means your rate of loading is so high. So this is what we just talked about in the previous slide, right? The diffusion rate versus the plastic flow rate, which is dominant. So whichever is faster will suppress the other. So we'll just look at the some of the constitutive relations. A general relationship between the flow stress and the strain rate at constant strain and temperature is given by sigma is equal to C into epsilon dot to the power m at constant strain and temperature, where m is known as strain rate sensitivity. Very important parameter is useful in the high temperature deformation. The exponent m can be obtained from the slope of a plot of log sigma versus log epsilon dot, similar to our Holomon equation. Here again it is epsilon dot. However, a more sensitive way is the rate change test, in which m is determined by measuring the change in flow stress brought by about a change in epsilon dot at constant epsilon and t, which is given by m is equal to dou ln sigma by dou epsilon dot at constant strain and temperature, which is equal to epsilon dot by sigma times dou sigma by dou epsilon dot, which is equal to del log sigma by del log epsilon dot. Suppose if you do it at two different strain rates, then it can be written like this. The final expression is this, which is very useful. That's what is written here. This is a more sensitive way of determining the m. So that means m is equal to log sigma 2 by sigma 1 divided by log epsilon 2 dot divided by epsilon 1 dot. Strain rate sensitivity of metals is quite low, less than 0.1 at room temperature, but m increases with temperature. Very important point. Okay, it is important only at high temperature deformation, as I mentioned, especially at temperatures above half of the absolute melting point, 0.5 tm. Above 0.5 tm, it is more significant. So this is what shown in a schematic here. Plot sigma versus epsilon. It's a test conducted at two different strain rates. So strain rate change test, or it is also called strain rate jump test to determine strain rate sensitivity. In hot working conditions, M values of 0.1 to 0.2 are common values. The above equation is not the best description of strain rate dependence of the flow stress for steels. For these materials, a semi-logarithmic relationship between flow stress and the strain rate appears to hold. So that means for materials like steels, this is relation holds better than the other equation. That is sigma is equal to K1 plus K2 ln epsilon dot by epsilon naught, where K1, K2 and epsilon naught are constants. So this is again another empirical relation we can use. Strain rate sensitivity is a good indicator of changes in deformation behavior, and the measurements of M provide a key link between dislocation concepts of plastic deformation and a more macroscopic measurements made in the tension test. Very important idea, we will see. It is known that the velocity of dislocation motion was very strongly dependent on the stress according to this relation. V is equal to A times sigma to the power M prime. Moreover, strain rate is related to velocity of mobile dislocation by this expression. This we have already seen. Epsilon dot is equal to rho B V. So from these previous equations, we can relate or rewrite this. 1 by M is equal to dou ln epsilon dot by dou ln sigma, which is can be written by using this. So dou ln V by dou ln sigma plus dou ln rho by dou ln sigma. So you can use this relation and then apply this relation, then you get dou ln V by dou ln sigma is equal to M prime. Or we can simply write M prime is equal to 1 minus M minus dou ln rho by dou ln sigma. Thus, if there is no change in the mobile dislocation density with increasing stress, M prime is equal to 1 by M. This hardly is a reasonable assumption. However, if 1 by M is plotted as a function of strain, the curve extrapolated to 0 gives a value close to M prime, determined from the edge fit measurements of dislocation velocity. While strain rate sensitivity may be quite low in metals at room temperature, in other materials it may be quite appreciable. The extreme case is a Newtonian viscous solid where the flow stress is described by sigma is equal to eta times epsilon dot. Okay. So we are now trying to relate this strain rate sensitivity with different temperatures. As the temperature goes up, the extreme case of strain rate sensitivity can be, which will describe the Newtonian viscous solid, which will obey this flow equation like this. Okay, and we, by comparison with the previous equation of strain rate sensitivity, we find that M is equal to 1. The high strain rate sensitivity is a characteristic of superplastic metals and alloys. So we are slowly taking this idea of strain rate sensitivity at moderate temperature to very high temperatures, and now we are trying to explain a new phenomenon called superplastic metals or superplastic behavior. Okay, so any material which exhibit high strain rate sensitivity is a characteristic of superplastic metals and alloys. Superplasticity refers to extreme extensibility with elongation usually between 100 and 1000% of elongation. Okay. We will see this little more detail. We will look at closely the phenomenon when we look at the high temperature diffraction. The next chapter we will see. But we are just introducing this concept because we are talking about effect of strain rate on flow properties. There also this idea comes in because we are bringing M value, that is strain rate sensitivity, and then high strain rate sensitivity is a characteristic of superplasticity. So superplastic metals have a grain size or interface spacing of the order of 1 micron. Testing at high temperature and low strain rates accentuates superplastic behavior. The large elongation results from the suppression of necking in these materials with high values of M. So this sentence is very important sentence. You have to pay a little bit of attention. A large elongation results from the suppression of necking. Okay, so we just looked at the necking phenomenon elaborately. So we have to suppress the necking. That means these materials should have high values of M. So high values of M also gives a indirect measure of resistance to necking. So this point you have to keep in mind. Any material exhibits a high value of M. That means this material has the highest resistance to necking. Then it will promote superplastic behavior. That means higher percentage of elongation. An extreme case is hard glass, where M is equal to 1, which is almost like a viscous solid, which can be drawn from the melt into glass fibers without the fibers breaking down. So this is one classical example where we can see the strain rate sensitivity is very high. So now we'll try to relate that with some basic equations. P by A is sigma, which can be related to this C times epsilon dot M, and we can rewrite this equation for the epsilon dot, and we can also connect the other definition of strain rate and then combine these two and get one a general relation for describing the strain rate sensitivity. So it is also will give another idea. The equation states that so long as M is less than 1, the smaller the cross-sectional area, the more rapidly the area is reduced. Okay, and this figure shows how the area decrease varies with M. So this is minus dA by dt, and this is area. So how the M value changes. For M is equal to 1, this is almost a constant here. Okay, there is no this area reduction takes place. Reduction is not an issue here. But on the other hand, if you have M is equal to 3 by 4, M is equal to 1 by 2, M is equal to 1 by 4, then you can see the influence of this area reduction. Okay. When M is equal to 1, the deformation is Newtonian viscous and the dA by dt is independent of A, and any incipient neck is simply preserved during elongation and does not propagate inward. Okay. So all this curves indirectly indicates the resistance to how the material resists to necking. Okay, this is what you get out of this at the end. And M approaches unity, the rate of growth of incipient necks is drastically reduced. Okay. Now we will pay our attention to temperature. So far we just looked at the strain rates, and now we look at the effect of temperature. The stress strain curve and the flow and the fracture properties derived from the tension tests are strongly dependent on the temperature at which the test was conducted. In general, strength decreases and ductility increases as the test temperature is increased. However, structural changes such as precipitation, strain aging, or recrystallization may occur in certain temperature ranges to alter this general behavior. So, you have to be careful in making this, making this statement. You have to see that the temperature does not influence any other phase transformation reaction or precipitation, strain aging. Just before we have seen simple, the pinning and unpinning of dislocation causes the strain aging behavior, and the recrystallization, grain growth. All these things you have to keep in mind. Thermally activated processes assist deformation and reduce strength at elevated temperatures. The best way to compare the mechanical properties of different materials at various temperatures is in terms of the ratio of the test temperature to the melting point expressed in degrees Kelvin. The ratio is often referred to as homologous temperature. See, this is one way of normalization we do. Okay, just to keep reduce the influence of melting point or suppress the influence of melting point. You refer to this parameter called homologous temperature, and then study the compare the mechanical properties of different materials. This also we will see it as we study this high temperature deformation behavior in detail. We will use only these parameters. That time also you will appreciate this much better. When comparing the flow stress of two materials at an equivalent homologous temperature, it is advisable to correct for the effect of temperature on elastic modulus by comparing the ratio of sigma by E rather than simple ratio of flow stress. So this is basically some of the instructions or informations when we take so much of information from the simple tensile test. So what are the aspects to look at? That is how these points are given here. So the temperature dependence of flow stress at constant strain and strain rate generally can be expressed by sigma is equal to C2 times E exponential Q by RT at the constant strain, where Q is an activation energy for plastic flow in joules per mole, R is universal gas constant, T testing temperature in Kelvin. If this expression is obeyed, a plot of ln sigma versus 1 by T will give a straight line with the slope of Q by R. So what is the point? The value of flow stress depends on the dislocation structure existing at the time the flow stress is measured. Dislocation structure will change with temperature, strain rate and strain. One way to separate these effects is to evaluate Q by a temperature change test. Okay. So if you conduct the deformation at different temperatures and then evaluate this, we can find out the Q, the activation energy, without the influence of the other dislocation, other parameters like dislocation substructures and so on. The stress strain curve is conducted at constant strain rate, and the desired value of plastic strain, the temperature is changed from T2 to T1. After the temperature comes to equilibrium, the activation energy is given by Q is equal to R ln Q sigma 1 by sigma 2 times T1 T2 by T2 minus T. So this is very important relation to find out the activation energy for the plastic flow. Activation energy for what? Activation energy for plastic flow under the influence of temperature, high temperature. So we will look at some of the constitutive equations which are very um, uh, useful or important for the further discussion in this subject. So what are constitutive equations? Constitutive equations describe the relations between stress and strain in terms of variables of strain rate and the temperature. The simple power law relationship like Holomon and its variants are elementary forms of constitutive equations. Okay. And early concept in developing constitutive relationship was the idea that the flow stress dependent only on the instantaneous values of strain, strain rate, and temperature. So this is a function which is dependent on our sigma epsilon dot t is equal to 0. This is directly analogous to the concept that a thermodynamic system in equilibrium can be expressed by the state variables pressure, volume, and temperature. So people try to derive a constitutive equation looking at all these aspects. So okay, it was a bit complex, and then some of the assumptions have been made, and then I'm not getting into the details, but I will give some simpler results reported in the literature. A much simpler but useful relation describes the combined temperature and strain rate dependence of the flow stress. Sigma is equal to F, a function of Z, which is F as a function of strain rate times epsilon to the power delta H by RT at constant strain, where delta H is an activation energy in joule per mole that is related to activation energy Q. Q is equal to M delta H, where M is the strain rate sensitivity. So these parameters you have seen already. A quantity Z called Zener-Holomon parameter. It may also be referred as temperature modified strain rate. Z is equal to epsilon dot times e to the power delta H by RT. See, this Zener-Holomon parameter is also very important parameter which describes the high temperature deformation or the temperature influence on flow properties of materials. Okay, these are all very key constitutive equations. That's why I just want to bring in. So the Holomon equation is described by this. A relationship which is particularly useful for correlating stress, temperature, and strain rate under the hot working conditions was proposed by originally Sellers and Tegart. So, which is reads like this: epsilon dot is equal to A times sine alpha sigma to the power n prime into e to the power minus q by RT, where A, alpha, and n prime are experimentally determined constants, and q is the activation energy. At low stresses, alpha sigma is less than 1. The above equation reduces to the power relation such as is used to describe the creep behavior. So normally this kind of expression is used in the creep behavior. We will see them later, but I'm just introducing here to make sure that how the temperature influence of flow behavior is addressed. So epsilon dot is equal to A1 times sigma to the power n prime into e to the power minus q by RT. And high stresses where alpha sigma is greater than 1.2, it reduces to an exponential relation like this. Epsilon dot is equal to A2 exponential beta b into e to the power minus q by RT. The constants alpha and n prime are related by beta is equal to alpha n prime. So that alpha and n prime can be simply determined from the test at high and low stresses. So if you follow this Sellers and Tegart's equation shown in the previous slides followed, the data will plot as a series of parallel straight lines, one for each temperature, when epsilon dot is plotted against sine hyperbolic alpha sigma on log coordinates. The activation energy Q can be obtained from plot of log sigma, plot of log epsilon dot at constant sine hyperbolic alpha sigma against 1 by t. Power relation has been shown to be valid over 15 decades of epsilon dot into exponential minus q by rt. So these constitutive relations have really worked for relating the stress, temperature, strain rate. Okay, so very important some relations. So we will use some of these relations and take it forward to describe high temperature behavior like creep and stress rupture and so on. Okay, so yeah, let us look at finally the effect of temperature, stress strain curves. The flow stress of metals increases with increasing strain rate and decreasing temperature, which is already known. And this is because of thermally activated dislocation motion is inhibited. And there is a famous equation called the Johnson-Cook equation, which reads like this. Sigma is equal to sigma naught plus k epsilon to the power n. This is almost like a Ludwig type of equation here, multiplied by 1 plus c ln epsilon dot by epsilon naught dot into 1 minus t minus tr divided by tm minus tr to the power n. So what is this? What is this equation tells? See, we looked at so far the flow behavior independently. Like initially we looked at simple room temperature deformation, and then we looked at the strain rate effect, and then we looked at the temperature effect. So everything is combined in one equation. So that is why this equation is quite popular and useful. So which is widely used in the large scale deformation codes. So in fact, it is being used in the large deformation codes. The three groups of terms in parentheses represent work hardening, strain rate, and thermal effects respectively. The constants K, N, C, and M are material parameters, and TR is the reference temperature. Tm is a melting point, and to the reference strain rate. The basic idea is to develop one equation that represents the mechanical response of a material from 0 Kelvin to 0.5 Tm, and from very low strain rates such as 10 to the power minus 5 per second to very high strain rates 10 to the power 5 per second. So this equation is powerful in that sense. It represents the material behavior, try to represent the material behavior with all these constraints, right? Strain rate, low strain rate to high strain rate, low temperature to high temperature, okay, and then involving work hardening, all of them. So this equation is also very useful to describe the material behavior. Okay. So I will stop here, and we will continue our discussion on the mechanical testing in the next lecture. Thank you.